Okay, thanks. Okay, so I'm going to talk about differential Chow forms and differential Chow varieties. And this is an overview or summary of the work on this topic that we did in the last 8 years since I was a first year PhD student. And all this, okay, sorry. All this I joined work with Xiaosheng, Chunming, Tom, James, they are here, and Yinghong Li. My talk consists of 4 parts. In the first part, I will give the motivation to study the problem. So in this part, I will give a brief introduction to the theory of algebraic Chow forms and Chow varieties. Then we move on to the differential Chow forms and differential Chow varieties. First in the ordinary differential case, and then in the partial differential case. So the last is the summary and some further problems. In the groundbreaking paper on the Chow forms and Chow varieties, Chow and Van Walden described their motivation in these words. So it is principally important to represent geometric objects by coordinates. And once this has been done for a specific kind of object, it is desirable to provide the set of objects with the structure of algebra varieties, so that we can characterize the set of objects by algebra equations. For the coordinate representations, there are some simple examples. So we are familiar with the Cartesian coordinates. So once we choose a Cartesian coordinate system, so each point in the space could be represented by its Cartesian coordinates. So we all know this. And for lines in the 3-dimensional projective space, they could be represented by their Blake coordinates. And further, for linear spaces in the n-dimensional projective space, they can be represented by the Grassmann coordinates. And we will take the Blake coordinates for an example to illustrate it in details, so that we could give a better understanding of the Chow coordinates later. So suppose V is a line in P3, so it could be defined by 2 linearly independent linear equations. And the Blake coordinates of the line is a point in 5-dimensional projective space. And it could be constructed by the coefficients of the defining equations of the line in this way. And if we consider all the lines in P3, then the set of their Blake coordinates is actually a quadric. And we call this quadric the variety of lines. And the quadric is just the parameter space of lines in P3. That means each point in the quadric represents a line in P3. And for algebra varieties, their coordinate representations are Chow coordinates. And the variety of algebra varieties are just the Chow varieties. And the rigorous definition for Chow coordinates and Chow varieties are based on the theory of algebra Chow form. And the theory was established in 1937 by Chow. V is a d-cycle in the n-dimensional projective space. So here, each Vi is a irreducible variety of dimension d. And we require Si to be the non-negative integers. So this is actually an effective d-cycle in algebra geometry. And for simplicity to give the definition of algebraic Chow form, temporarily we suppose V is an irreducible variety of dimension d. Given d plus 1 number of hyperplanes in this way, and we want to know what's the conditions on the coefficients of the Li such that V and the given D+1 number of hyperplanes have a non-empty intersection. And the condition is actually described by a hypersurface. And the defining polynomial of the hypersurface is defined to be the Chow form of the variety. So the vanishing of the Chow form on the coefficients of this Li gives a necessary and sufficient condition for the variety and the D+1 hyperplanes have a non-empty intersection. Then the coefficient vector of the Chow form of the variety regarded as a point in a higher dimensional projective space, depending on how many monomials in the Chow form, the basis of the Chow form. And this coefficient vector is called the Chow coordinate of the variety. And the most important invariant of the variety, namely the degree of the variety, could be read off by the degree of the Chow form. And the degree of the variety is also equal to the number of linear factors in the Poisson product formula of the Chow form. And the geometric meaning of this number we take d equal to 0 for an example. By factoring the Chow form, we can get all the points of in the variety. So the coefficients of the linear factors, the G points are all the points in the zero-dimensional variety. And okay. And for the Chow form of a D cycle, it is the product of the Chow forms of Vi with multiplicity Si. So once we define the algebra Chow form for a D cycle, the Chow coordinates and the degree of the algebra cycle could be defined in a similar way. And we consider all the D cycles of degree G. Then the set of their Chow coordinates is actually a variety in the projective space. And this fact was proved by Chow in 1937. And this projective variety is just called the Chow variety of index D and G. That means the Chow variety, the Chow varieties are just parameter spaces for cycles of fixed dimension and degree. The Chow forms and Chow varieties are basic concepts in algebra geometry, and the research on Chow forms and Chow varieties is still active now. And the study mainly focuses on three aspects. For the numerical study of Chow varieties, we are interested to give to estimate the bounds on the degree and the dimension of the Chow varieties, and also to construct defining equations for the Chow varieties. This problem is very difficult because of the complicated structure for Chow varieties. Even for the Chow varieties or curves, it is already very difficult. And for the structures, it's not so clear until now. And in the computational aspects, these people did a lot of work on the computational complexity of the Chow forms to devise algorithms to compute Chow forms and find new formulas to compute Chow forms. And regarding applications, Chow forms and Chow varieties have a lot of applications in computational algebra geometry, in intersection theory, and also in number theory and so on. So for example, Brown-Wheel made a major progress in the effective non-analysis by analyzing new properties of the generalized two forms. We work on differential algebra, and first, the basic geometrical objects are differential varieties. So we are interested to study the coordinate representations of differential varieties, and further provide the a specific kind of differential varieties with the structure of differential varieties. That's what we will do here. And our work on ordinary differential two forms is the first, is the beginning of such study. Suppose V is an irreducible ordinary variety of dimension D and order H, and we still consider D plus 1 differential hyperplanes. Here, differential means all the differential variables y1 to yn are differential variables. And we consider the same question when V and these D plus 1 differential hyperplanes have a non-empty intersection. And for the ordinary differential case, it is not that easier. And because in algebra geometry, for the intersection theorem is essential to give the definition of algebra two form. But in differential algebra, Rita gave a counterexample to show that the intersection theorem is invalid in differential algebra. So we need to develop new tools. We first proved the generic differential intersection theorem. And by this theorem, we can show that in the sense of Cauchy closure, the condition is given by a general component of an irreducible differential variety. And we call this irreducible polynomial the differential two form of the variety. And the coefficient vector of the differential two form is defined as the differential two coordinate of the irreducible variety, differential variety. Here is a simple example. In this example, V is defined is a linear differential variety defined by this linear differential equation. And the differential two form of the variety is a polynomial of degree 2, this polynomial. And the differential two coordinates of the differential variety is this point, a point in the 9-dimensional projective space. The differential variety, the differential two forms have similar properties to the properties of the algebra two forms. And through differential two forms, we can introduce new invariants for differential varieties. Of course, first it can reflect the known invariants of the differential varieties. So the first property shows that the order of the differential two form is equal to the order of the differential variety. And the differential two form is differentially homogeneous of the same degree in each set of in each coefficient set of Li, is Ui. And we define the degree as the differential degree of the variety, the differential variety. And we also have the Poisson type product formula. And here, this is the eighth derivative of the linear vector. And the number of linear vectors has the similar geometric meaning to the degree of algebra varieties. We call it leading differential degrees. And if a differential variety has a differential dimension D, order H, differential degree M, and the leading differential degree G, then we call this differential variety is our index DHGM. These are four important invariants for differential varieties. And we can, through differential two forms, we can define differential cycles. So that's here, Vi is not only required to have the same differential dimension, but also should have the same order. So that the differential cycles and the Chow forms have a one-to-one correspondence, and also has isomorphism as groups. And we can also define differential Chow coordinates and the index for differential cycles through its differential Chow form. And if we consider all the differential cycles of the same index, and we define if the set of their differential Chow coordinates is a differential constructible set, then we call it a differential Chow variety. And we see for the index DHGM, the differential Chow variety exists. This definition is reasonable because in algebra geometry, if we consider the Chow variety for algebra cycles in the affine space, it is also not projectively closed. It is a constructible set. So for differential varieties in the affine space, we also define in this way. And for the existence of differential Chow varieties, we first proved its existence for the case G equal to 1 with a constructive proof. But the proof couldn't be adapted to the case G greater than 1 because we don't have a hybrid elimination algorithm to eliminate the differential variables and algebraic variables together. And then I forgot in which year Xiaoshan went to a conference held in UK, and there he presented our work and also proposed this open problem. There, a model theorist told him this problem may be closely related to the elimination of imaginaries in DCF. Then, after he told me this, I read the papers on elimination of imaginaries and found it actually it doesn't work. But the good thing is it reminded me that the model theory may be of help to this problem. So in 2014, I went to UC Berkeley to visit Tom for 1 year. And there we finally solved the problem with a model theoretical proof. So this is the theory for ordinary differential Chow forms and ordinary differential Chow varieties. And around the differential Chow forms, we have further results. In theoretical aspects, we also established the theory of projective differential Chow forms. And here is open problem. We call it the differential completeness of projective differential Chow forms. And we only proved it for several few cases. But for the general case, we cannot solve it now because the projective differential space is not differentially closed. And we also developed the theory of ordinary difference Chow forms. But this for the difference case, things become worse. Even for difference Chow coordinates, we couldn't define, because in the difference case, for one just irreducible difference polynomial, there may be several general components. So in this case, it may happen that several irreducible components of the same irreducible polynomial may have the same ordinary difference Chow form. So the Chow coordinates could have been defined in this case. Sorry. And in the computational aspects, we devised the two single exponential algorithms to compute differential Chow forms for prime differential ideals in this form. But for the general varieties, we couldn't devise algorithms to compute it right now. And regarding applications, we first used the generalized differential Chow form to give a rigorous definition of differential resultant. And also we used it to give optimal, not optimal, just lower degree bound for Lura generators. Now we move to the partial differential case. And we also suppose, So here we suppose there are m derivation operators, and m is supposed to greater than 1. And suppose V is a irreducible differential variety of dimension d. We also consider the conditions such that V and these d+1 differential hyperplanes have a non-empty intersection. So with the generalized partial differential generic intersection theorem, we can show this set S is actually an irreducible differential variety of codimension 1. But in the partial differential case, we encountered an obstacle to define partial differential Chow forms. And this obstacle couldn't be overcome because it may happen that S then doesn't exist a single polynomial f such that S is the general component of this polynomial. So like this example shows. And we stopped thinking this, and then in last year when I went to a conference a program on modular space in Italy. There, a speaker reminded me that even even we couldn't define partial differential Chow forms for every irreducible partial differential variety, we could. It is meaningful to think for which varieties the differential Chow forms exist. So now give a sufficient condition. If the partial differential variety has the quotient polynomial in this form for some d and s, then the partial differential Chow form exists. And if it exists, it has the order of the not the order, just the order of the partial differential Chow form is equal to this number. And we proved it is partial differentially homogeneous or the same degree R in the coefficient of each Li. And we define this number the differential degree of the variety. We conjecture it is also a necessary one. Yeah, the theorem used to be given a necessary and sufficient condition, but found there is a gap in the necessary part, and we cannot fix it until now. Okay, let's get back to the problem proposed by Chow and Van de Walden. Here, first, the specific kind of objects are irreducible differential varieties with quotient differential polynomial in this form and differential degree R, and we consider this set. And also with the model theoretical proof, we can show this set is a differentially constructible set. Okay, let's summarize the results we got and propose new problems. So we established the theory of ordinary differential Chow forms and ordinary differential Chow varieties. But for the partial differential case, just very limited results are obtained. And for the problems left open now. They're mainly concern the following ones. So for the ordinary differential case, we care about the differential completeness of the projective differential tool forms, and devises more efficient algorithms to compute differential tool forms for general differential varieties. And although we have proved the existence of differential tool varieties with a model theoretical proof, but we are still interested to find a constructive proof for it, because only we can construct the differential tool varieties, we could study the structure of differential tool varieties. And for the partial differential case, we want to prove the condition we give for the existence of differential tool forms is actually a necessary and sufficient condition. And further, we want to know how to give coordinate representations and parameter space for general differential varieties. For even at least for more general cases than what we did before. So this is the reference. Thank you for your attention. Hi. Oh no, for the linear case, it is what? Okay, so you want to know in the partial differential case, what's the advantage for the linear case, right? No, it is the answer is there's no any help for the linear case. Even of course we care about the differential resultants, right? But even for the linear partial differential case, we couldn't define it right now. It's not differentially complete in it. Yeah. Yeah, at last October when in Dart 7, I talked with William Simmons, and it is not a counterexample for the conjecture. Yeah, we still think about it now. Okay, thank you.